Okay, so here's our problem. We have this triangle and these two parallel lines denoted by the arrows. We're told that this triangle has an area of 8 cm squared. This triangle has an area of 16 cm squared, and we have to find the area of this triangle, which I've decided to call X. Right, how are we going to do this? Well, it turns out it's actually a scaling problem. If we look at these two triangles, we notice that the area of one is twice the other. And if you look at them like this and treat this as the base, then they have the same height, okay? So looking at it like that, same height from P to Q, okay? And one has twice the area of the other. So let's look at the formula for the area of a triangle. Okay, area of a triangle is half base times height, okay? Now, they've both got the same height from P to Q, again, looking at it like that, okay? So if they have the same height and one has twice the area, that means it must have twice the base of the other, okay? Which means that if we call P to N A, that's the base of triangle A, that's the base, P to Q is the height, okay? Then P to L must be 2A, right? I'll just go over that again. Formula for the area of a triangle is half times base times height, okay? And if two triangles have the same height, which these two do, then if one has twice the area of the other, it must be because their base is twice as big. So we've worked out that P to L is twice N to P. Okay. Now we look at the whole thing. Okay. Triangle NLM. The whole thing and NPQ, this small triangle, are similar triangles. That means the angles are the same. So that angle is the same as the whole thing's angle. Obviously, it's the same angle. But that angle there is the same as that angle there. And the ratio of the three sides is the same. They're different sizes, but the ratio of the sides is the same. For example, the ratio of N to Q to N to P is the same as the ratio of N to M to N to L. Okay? So we can work out the area of the big triangle using that information because we know the area of the little triangle. Right. Do it like this, okay? We have the little triangle and we have the whole thing. So that's N, P, Q, and the whole thing is N, L, M. Right. Introduce something which I call D, okay? D is just a one-dimensional quantity which shows you the ratio of the one-dimensional quantity of these two to each other. That didn't sound brilliant. What I mean is that the one-dimensional ratio of the small triangle to this triangle was 2 to 1, okay? I called that side A. We don't know what A is, it doesn't matter, it's 2 to 1. So I'm talking about the ratio of this side, for example, of the little triangle to the whole thing. The whole thing is A plus 2A is 3A, okay? So the ratio of a one-dimensional quantity, doesn't matter which one, we've chosen this side, we could have chosen that side or that side, it doesn't matter, but it's very convenient to choose this side for this problem. The ratio is 1 to 3, okay? It's a one-dimensional quantity, meaning it's a side. It's not an area or a volume, it's a side. And it's 1 for the small triangle, okay? to 3 for the whole triangle. Okay. Now, the reason we're interested in this D thing is because it tells us the one-dimensional scaling factor, okay? And to go from there to there, we have to multiply by 3, okay? And that's why we're interested in this quantity. It tells us that the scaling factor, the one-dimensional, the D scaling factor is 3, okay? And from that, we can work out the area scaling factor. And that's going to take us from the area of the small one to the area of the whole thing, which will, because we know these areas, will tell us x very quickly. We're interested in the area of the whole thing. So now we write down A, which is a two-dimensional quantity. A has units, look, cm squared, it's two-dimensional, okay? And write down the area of the small triangle. Well, it's 8. Okay? And we want to know what goes in there. We want to know the area of the big triangle. And the question is, what do we multiply 8 by to get the area of the big triangle? Well, this is why I introduced this weird quantity, D, this strange one-dimensional thing. It's purely just to get the one-dimensional scaling factor, okay? Because once we know that, we know the two-dimensional scaling factor. What do we multiply the 8 by? It's easy. It's the one-dimensional scaling factor squared. Okay? I'll just go over that again. Once you know the one-dimensional scaling factor, you immediately know the two-dimensional scaling factor. It's quite simply the one-dimensional scaling factor squared, which is 9. 3 squared is 9, of course. So therefore, we're going to multiply by 9. 8 nines is 72. And that's how we work out the area of the whole thing, okay? It's 72 cm squared. It's the whole triangle. And just quickly, I know this isn't part of this problem, but it's likely you'll get a problem involving volume in your exam. The volume scaling factor, okay? Whatever the volume of that is, to find the volume of this, I'm sure you've guessed, you multiply by the one-dimensional scaling factor cubed, which in this case is 27. Whoops, 27. Okay, don't worry about that for this question. That's just the general case, okay? Right, so we've pretty much done it. The area of the whole thing is 72, so therefore x is 72 minus 8 minus 16, which is 72 minus 8 is 64, 54, 48 centimeters squared. There we go, 48 cm squared. Okay, that's how it's done. Scaling factors.